A single stream of cars, each of width A and exactly in line, is passing along a straight road of breadth B with uniform speed V. So basically what we have here is a road with two sides of the road like this, and we have a stream of cars which is traveling in one direction on the road, and the speed of each car is V, and the distance between successive cars is C, and the width of each car is A, and the breadth of the road is B. So this is the geometry of the situation. Now part A is asking us, a squirrel crosses the road safely at a constant speed u in a straight line, making an angle theta with the direction of the traffic. And we are asked to find the minimum possible value of u, that is the minimum possible value of the speed of the squirrel for which it will cross the road safely. Okay, and the second part of the question is, if the squirrel chooses theta and u so that it crosses the road at the least possible speed, that is the speed in which we will derive in part A, then we have to find the time it takes for the squirrel to cross the road. So let us focus on the first part of the problem to start with. We have been asked to find the minimum possible value of u. Now stop and think for a moment. The minimum possible value of u, that means the slowest possible speed of the squirrel for which it will safely cross the road. That is what we are required to find out. Okay, so for example, if say, forget about the cars for a moment and say the squirrel starts somewhere from here and takes this straight line path at an angle theta. Now we have to, and it travel at a constant speed of u. Now we have to find the minimum possible value of u for all possible configurations. We have to find the minimum possible value of u so that no car hits the squirrel. Okay, now first of all, let's understand the geometry of the situation better, because this is a dynamic situation and you will have to do some bit of visualization here, now how the squirrel is moving and how the cars are moving. So let us define the direction in which the cars are moving as the x direction, and let us define the direction perpendicular to the road as the y direction. Okay, now we have this stream of cars traveling along the road where the width of each car is a, and I have assumed this red path to be the path taken by the squirrel to cross the road. Now ask yourself this question: what is exactly the risky part of the squirrel strip? What is that part of its path on which there is a chance of collision with a car from the stream of cars? Obviously that part is from this point here to this point here. So let's call this point x and let's call this point here as y. Okay, so this segment xy is the risky part because any point on this segment lies directly in the path of the stream of cars. So first of all, we have been able to observe that make the observation that xy is the risky part of the squirrel's path. Now secondly, also think about another important point. What do you think is the squirrel's general direction of travel? In the sense that, do you think that the squirrel's velocity will have an x component parallel to the movement of the cars or anti-parallel? So what I'm trying to say is that, assuming that the cars are moving in this direction as I have drawn here, do you think the squirrel will take a path like the red path I have drawn here, or will it be moving in this direction so that its x component of its velocity is anti-parallel to the direction of the movement of the cars? Now what we really need to find is the minimum possible value of u. So this means that if the squirrel's x component of velocity was anti-parallel to the car's velocity, for example, the cars are moving this way and the squirrel is moving in some direction like this, then it would have to move really fast to traverse the risky part. So let's draw that situation again. So we have this road and we have this stream of cars, right? And assuming that the squirrel was moving so that the x component of its uh, velocity was anti-parallel to the movement of the cars like this. So the risky part is this segment, right? Now the cars are moving this way and the squirrel is going this way. That means it would have to move really fast to avoid a collision with the incoming car. So it would have to move really fast to traverse the risky part. Whereas what we require is the minimum possible velocity, the slowest possible speed of the squirrel. So we conclude that the squirrel's velocity's x component is parallel to the movement of the cars. So it will move along the red, somewhat like the red path I have drawn here. Okay, so basically the x component of its velocity will be parallel to the direction of movement of the cars. Yeah, it will be safer even if the squirrel is slower that way. So you might like to think of yourself trying to cross a busy road between slow moving cars. How would you cross the risky part? Would you travel towards an incoming car like what I've done here, or would you move away from the incoming car? The incoming car is this car here, and would you move away from it? Obviously you'd move away from it so that your general direction of displacement is the same as that of the cars. So we have established one point that the squirrel's x component of velocity is parallel to the direction of movement of the cars. Now let us analyze the situation more deeply. So let us draw the figure once again, the figure of the road and the cars and the squirrel. Okay, so we have the road and we have two successive cars. Okay, and let us name the cars through which the squirrel passes as, say, F and B. So F I'm naming the front car and B as the back car. So this is how I have chosen these two letters. F is the car behind which the squirrel will enter the risky part. So if this here is the squirrel's path, okay, and the risky part is this segment, then basically the squirrel enters the risky part at the point X behind the car F, and it exits the risky part at the point Y, that is in front of the incoming car B. Okay, and the incoming car B is the real villain here, because that car is the one which is likely to hit the squirrel. Now close your eyes and imagine the situation carefully. Assuming that the squirrel is moving at the slowest possible speed, we would really want that the squirrel should be placed at the maximum possible distance from car B as it is entering the risky part. Okay, because car B is the one which is likely to hit the squirrel. So when it is entering the risky part, the squirrel should be placed at the maximum possible distance from B. Okay, and ideally that distance should be the distance between F and B, that is this distance, because this is anyway the maximum possible distance. So the squirrel should enter the risky part just behind F. That means F is moving away like this and the squirrel should enter the risky part just at this point. Okay, and then it should move like this. So there's a lot of visualization going on here. I'm warning you, what is really required on your part here is to imagine this synchronized movement. The squirrel is also moving and the cars are also moving. Okay, and you have to assume that situation where the squirrel enters the risky part just behind the car F, so that its starting distance from the car B is the maximum possible, it is at its maximum possible value, which is C units. Okay, and having understood this, we also make the second important observation, that since the squirrel is moving at the slowest possible speed, that means when the squirrel is exiting the risky part, the incoming car B will almost be touching the squirrel as it is exiting the risky part, right? If the squirrel had been any slower than the minimum possible speed, then the incoming car B would have definitely hit the squirrel. But since the squirrel is fortunately moving at the minimum value for a safe velocity, it will just exit the risky part without car B hitting it. So now, having made these two observations, let us draw the diagram once again, one final time, and then we will be able to proceed with the problem solving. So we have this as a road, and what I do is I draw the path that the squirrel will take. So let this path be the one that the squirrel takes at a speed u, angle theta. Okay, so let x to y be the risky part. So what I observed was that x is the point just behind F. So the original configuration of the cars would be that the car F would be here, okay, and the car B would be C units behind F, like this, so that the squirrel is initially at the maximum possible distance C units from B. Okay, and when the squirrel is exiting the risky part, at that moment the car B is just at this position, about to hit the squirrel here, and obviously the car F has moved somewhat ahead on the road. So these are the two snapshots of the cars. Now when the squirrel is entering the risky part, then it is at this point X, just behind F, and when it is exiting the risky part at Y, then it is just in front of the incoming car B. Okay, so that means that what we really want is that in the time that the squirrel crosses the risky part, assuming that that time is t is the time that the squirrel takes to cross the risky part. So in that time, the front of car B should have moved a distance which is less than this distance. Okay, this distance from the original position of the front of B to that position at which the squirrel is exiting the risky part. So what is this distance? So we have, this is C, okay, and this distance here would be the projection of the distance covered by the squirrel on the risky part, the x projection of that. So if t is the time taken to cross the risky part, then ut is the distance traveled by the squirrel along the risky part. That means this projection here is ut cos theta. That means this red segment here is C plus ut cos theta. That means the front of car B should have moved a distance less than this to avoid a collision with the squirrel. Okay, which finally means that the front of the car in time t, it will have moved a distance vt, because v is the speed of the car. That means vt should be less than c plus ut cos theta. Okay, and we have another constraint on t, because the width of the cars is a. That means the horizontal component of the car's velocity, the y component, not the horizontal, the y component is u sine theta. That means u sine theta into t should be equal to the y distance covered in that time, which is a. Okay, so these two give us the possible constraints on t, and you can easily manipulate these, and I will leave that as an exercise to you because I've done the most important part of the problem solving. So you can easily show from this that u should be greater than or equal to av by c sine theta plus a cos theta. That means the minimum possible safe value for u for the speed of the squirrel is this. Okay, and if the squirrel is moving at a speed greater than or equal to this velocity, then it can safely cross the road without colliding with the incoming car. So this is the first part of the problem. Now the second part says that if the squirrel chooses theta and u, so it chooses theta and u so that it crosses the road at the least possible speed. Okay, then find the time it takes to cross the road. So we come back and we now have to make use of this result that we've obtained. So we observe that the minimum value of u min, if I denote it by u min, then this will be equal to, v is a constant, a is a constant, so when the denominator is maximum, so u min will be equal to av by c sine theta plus a cos theta, the maximum value of this. Okay, and now you can easily show that the maximum value of this is equal to will be obtained when tan theta is equal to c by a. You can show it by a simple differentiation of this expression and equating it to 0. So tan theta theta is equal to tan inverse c by a. When that happens, then u is at its minimum possible value. So if t is the time that is taken to cross the road and b is the breadth of the road, then obviously t will be equal to b by the y component of the velocity of the squirrel, so b by u sine theta. So this will be b by c sine theta plus a cos theta by v sine theta av sine theta when theta is equal to tan inverse c by a. Okay, so if I divide sine theta from the numerator and the denominator, if I divide by sine theta, I have b times c plus a cot theta by av when theta is equal to, or when tan theta is equal to, or theta is equal to tan inverse c by a, or tan theta is equal to c by a, or cot theta is equal to a by c. So we have this as b by c plus a square by c by av. So finally we obtain the value of t as b by v, and if I write it in a more symmetric form, c by a plus a by c. So this is our final answer for the time.